My name is Shreya Arora with registration number 16BCM0086, and I will be doing a lecture on free particle in a one-dimensional box. So first we consider an infinite potential well in which we have a particle. Assume that the particle is moving in the x direction from x equals to 0 and x equals to a. And it is restricted by the walls x equals to 0 and x equals to a. So now for this to be possible, we have to assume that the particle does not lose energy when it collides with the boundaries, and so that means that the energy that the particle contains remains constant. We also know that the potential energy inside the well is going to be equal to 0, and the potential energy outside and on the wall is going to be infinity, or infinite. And then we also have this another idea, which is the idea of finite potential well. We cannot consider a finite potential well in this situation, because when you have a finite potential well, you have residue outside the potential well, which means that there's a chance that the particle can be outside the well or on the wall. So therefore, what we do to fix that, theoretically what we can do to fix that, is that we extend the length of this well to infinity, which means that the residue will slowly decrease, suppose like this, eventually becoming the wall itself, therefore becoming an infinite potential well. So now that we know this, we know that the particle is definitely present inside the potential well. So we can start to do the derivation of the eigenenergy values and the eigenwave function. So what we consider first is the equation for the potential energy present inside the infinite potential well. So we know that phi is equal to AEI to the power of AE to the power of IKX plus BE to the power of IKX. So what we do is we double differentiate this, from where we get d squared of phi by dx squared, which equals to negative k squared phi of x. Now phi of x being this equation itself here. And then we also know that k is equal to square root of 2 me divided by h cross. So what we do is we basically move this over here, and we put the value of k inside. So we get d squared phi of x dx squared plus 2me, since it was k squared, divided by h cross squared phi of x, which equals to 0. Now with this function, we know that a solution of this function is definitely going to be phi of x equals to a sine kx plus b cos kx. So now that we have this function, what we do is we take the values at the walls of the infinite potential well, and we substitute them in here. So suppose for this point here, we have x equals to 0 and phi of x equals to 0. So that gives us 0 equals to a sine k into 0 plus b cos k into 0. Now we know that sine of 0 is 0, so that value cancels out, and we know that cos of 0 is 1. So we know that, so from that we get b equals to 0. Then we do the same thing for the other side, where we substitute in x equals to a and phi of x equals to 0, since it is possible to find the particle there. So from that we get 0 equals to a sine k of a. Yeah, ka. Now a cannot equal to 0, because if a equals to 0, that would mean that the entire probability function just equals to 0, which is not possible. So therefore sine of ka has to equal at some point. So that means that k of a equals to n pi, because sine equals to 0 at n pi. So which shows us that k equals to n pi by a. We also know, previously as shown, k equals to square root of 2me by h cross. So we have square root of 2me by h cross, which equals to n pi by a. So therefore energy equals to n squared pi squared h cross squared divided by 2m a squared. This is the eigenenergy equation. And in here, n has to equal to, basically n can equal to 1, 2, 3, or any other values. After that, it just cannot equal to 0, because that would mean that it violates the uncertainty principle. And now this equation has a very big importance, which is that it shows us that energy is quantified, because it basically shows us the entire spectrum of energy. For example, if you take n1, then you would have energy equals to E1. If you take n2, you would have energy equals to 4E1 since it's n squared. If you take n3, you would have energy equals to 9E1, and n4, it would be energy equals to 16E1, and so on and so forth. So you can actually draw this as a diagram where you would get, suppose this is E1, then this would be 4E1, this would be 9E1, this would be 16E1, and these three would represent the excited state, and this would represent ground state. So from this, we can also derive the eigen wave function. Since we still have a value of a missing that we do not know in the function, what we do is we go on to derive that, from which we would get the wave function. So we know that phi of x equals to a sine of n pi by a x. So this is basically substituting in the value of k that we found, and we know that b is equal to 0, so there's no need to include that part in there. So now what we do is we do normalization of this function. So we take the integral from 0 to a of phi into phi star dx equals to 1. So after and then what we do is we substitute in for this phi and phi, the phi star. So we get a squared for integral of 0 to a of sine squared n pi by a x dx. After we solve the integral, what we get at the end is a squared small a by 2 equals to 1, which means that big A equals to the root of 2 by small a. Now this is the normalization constant which we get, and now what we do is we basically substitute this back inside. So we get phi equals to square root of 2 divided by a sine n pi by a of x. So what this equation basically shows us is the wave function for the particle in a box. We can draw this out where it becomes like this. So for n equals to 1 and energy 1, you would have a wave like this. Then for n equals to 2, you would get a wave such as this. For n equals to 3, you would get a wave like that. So that is the graph of phi, which basically just shows us the wave function of the particle in a box. Now what we can do, we can also draw a graph of the absolute value of phi squared. Now since phi has been normalized, the absolute value of phi squared actually shows the probability of the particle. So for n equals 1, it would just be like this. For n equals 2, it would be such as this, and it would not go down because it's an absolute value. And then for n equals 3, you have 3 points like this, and this shows the probability of the probability density of the particle inside the infinite potential well. So from the eigenwave function, we have two important points that come out. First is that at the walls, which is over here, you will always have a node where the probability is 0. So which means that you will not find the particle at the probability density is 0. So you will not find the particle at the walls at all. And then the second point is that n minus 1 represents the number of nodes that are present in each energy level. So this shows that there's superposition occurring, which means that there is stationary waves present there. So this actually points out that the particle oscillates back and forth inside the box very quickly. That is all. Thank you.